last example, we considered this integral and saw geometrically that it would make sense to define it this way. And so now we'll put it in a definition. We'll do this case and two other cases, but based on the same principle. So first, these are called improper integrals. I'm going to use type 1 for the ones like that one that have infinity or minus infinity as bounds. I'm going to assume f is continuous. Then the integral from a to positive infinity is going to be the limit. I'm going to change that infinity bounds to a t. T goes to positive infinity. So if the bottom bound is minus infinity, I'm going to do a similar thing. I'm going to replace that minus infinity by t and send t where I want it to go. So here, if I have minus infinity to b, so in this case, I replace the bottom bound, which was minus infinity, by t, and then send t to minus infinity. So if these limits give us a finite number, we'll say the interval converge. If they give us infinity, d and e, or minus infinity, we'll say they diverge. So these integrals converge if the limit gives a finite number, otherwise they diverge. Right, so we have converge and diverge. You could also use exist or does not exist, but I like converge and diverge because some teachers like to keep does not exist for cases other than plus infinity and minus infinity. In this case, if you get plus infinity, the integral diverge for sure. All right, so we have a third case. We have the case where both bounds are infinite. Now, if both bounds are infinite, what you do is you split it into two integrals, one with minus infinity to a finite number, another one from that finite number to plus infinity. If both parts give you finite numbers, then you could add them and get your integral. So, let me see how I set it up. Okay. So if both the integral from minus infinity to a and the integral from a to plus infinity, if both of these converge, then we say, the integral from minus infinity to plus infinity would be equal to the sum of the two. So both are finite numbers, so we can just add them up. And we'll say that that integral converge. As soon as one of these diverge, as soon as one is plus infinity, minus infinity, or d and e, then this one would diverge as well. All right, let's do a problem. So I have the integral from 4 to plus plus infinity 1 over x 6 dx. This is an improper integral because I have infinity here. It's not a definite integral. You cannot apply FTC to it. We need to use this type of definition with limits. The 4 doesn't give us a problem, but the plus infinity does. So I'm going to replace that by t, and then say t goes to positive infinity. 1 over x 6 dx. At this point, I have a nice definite integral on which I can use FTC since this function is continuous. So I'll get the limit as t goes to positive infinity, x to the minus 6, so minus 5 over minus 5 from 4 to t. So what do I get? I get the limit as t goes to positive infinity. I get minus 1 over 5t5. If I plug in infinity into this, I get minus 1 over infinity to the 5, so I'll get 0. And then I have plus 4 to the 5 times 5. What is that equal to? So 4 to the 5 times 5. I get 0 plus 1 over 5, 1 to 0. And so the answer is 1 over 5, 1 to 0. Alright, so the steps are always the same. You need to first, before you apply any techniques of integration, before you use FTC, you need to replace the plus infinity by t. Then you can use FTC. You find your expression for the integral with the t. Then you apply the limit, and you get your number. Or you get plus infinity, or you get minus infinity, or you get d any.